All right, good afternoon. Welcome to webinar number 5. My name is Jake Beers, Elementary Science TOSA, or Science Specialist for Springdale Public Schools. And today we're going to be talking about the engineering design process. So this is the 5th in our webinar series. We've talked about unpacking the 3 dimensions of NGSS, the science and engineering practices, the CER framework, the 5E instructional model. And as I said, today we're going to be focusing on the engineering design process, wrapping up our series next month, talking about formative assessments and the role they play in science. So if you missed any of those webinars, you're welcome to go back. They're all archived and they're viewable on our professional learning page for both Springdale members, Springdale teachers, and educators outside the district. And again, you can watch the webinars. There's also usually a PDF of the slide presentations that you can check out there. So today, our goals for this webinar are just to talk about research around STEM and engineering education, and then explore some resources that you guys can use in your classrooms that are either already in our curriculum guides or that are outside that you can incorporate into your greater learning. So when you think about STEM education, you think about engineering, one of the things that we think about is problem solving. And our daily life requires problem solving. Well, most of us are solving small problems throughout the day, but sometimes bigger problems arise. And when we solve these problems, we have to use a lot of thinking. A lot of times there's a structured thinking to that. So my problem starts with this. Not that long ago, my wife showed up at our house with these 4 chickens. None of us had chickens before, and we had to figure out what we do with these chickens. So I researched and I went out and looked for data. I made a plan. We decided the type of chicken coop we need. We determined the needs of chickens. We did some reading, some research, looked at some building plans, and figured out a way to find a home for these chickens. So we started construction. Obviously, throughout as we go, we build, redesign, modify, because our plan wasn't going to be exactly like ones that we had found online. With some help from a couple helpers, we were able to build a chicken coop. So though this is a small, silly illustration, it kind of talks a little bit about what we do in the engineering design process. And so the engineering design process is an iterative process, which means that it goes on, or it can continue through cycles. That we're going to look at a couple examples. This one's from EIE, Engineering is Elementary, and they have some key pieces of ask, what's the problem, imagine what are some solutions, plan, build, test it out, and then make it better, try it again. And so in my plan, when I looked at the options that I did, I had to go through some of those similar steps. We've also created a few of our own. This is a modified version that the U of A STEM education team in Springdale Public Schools worked to create, having some of the similar steps. And then this one's from the Design Squad team out of PBS. This is the one that we prevalently use in our curriculum, in our Picture Perfect curriculum. So again, it has identify the problem, brainstorm, design, build, test, evaluate, redesign. This is where that cycle comes in, and then you share solutions at the end. So if we were to compare this cycle to my chicken example, so my problem was I had chickens and I had no idea what to do with them. So we brainstormed, we researched, we planned, we then designed a coop. That was a design that we modified. Then we began to build. As we built, we modified, tested, worked correct to see if it would fit, see if it would work. And then in the end, we shared our solution. Our chickens lived in our coop. So again, this is a small, simple example of what that problem looks like. But again, engineers, people who work to solve these problems work on a maybe a much larger scale, or even on a smaller scale when designing a product or improving a product. They follow a similar plan. Now remember, just like the science method, you don't always have to do every step. The scientific method is not used by every scientist. They're just a one way to frame the thinking. I don't think it's important that students memorize every step. They just need to know the process. So we're going to emphasize that it's about the process and not the end product. In the end, we get some eggs, right? So it's a good deal. So we're going to watch a short little video that's from Design Squad. We're going to be looking about how they use this design process to build the balloon car.
I'm Nate from Design Squad, and I'm here with Desi, AJ, Zara, and Anna.
All of us are designing different balloon cars.
It's got a carton for a body, half a plastic cup, 4 foam balls for wheels.
I think big DVD wheels will roll really easy.
Go! When we release the balloon, the rubber on the balloon squeezes the air out, which makes the balloon go.
And it goes everywhere and it's crazy.
Now we're going to add a straw, because what it does is it makes the balloon go from going in a crazy direction to a straight direction. The propulsion technology we're using here is a lot like a jet or a rocket. When the balloon squeezes air out the nozzle, it makes thrust in the opposite direction that makes the balloon in the car want to go that way.
Racers ready. On your marks. Get set. Go!
I just can't get mine to go straight.
I don't really think it was because it would go like that. I think it was because it would go like that.
I think you might be onto something. This side-to-side motion made it not go straight. So I took this front axle and I changed its angle just a little bit, so hopefully it corrected it, and now it goes straight. AJ, I challenge you.
Racers, get your engines pumped. Go! Ah!
Good race.
Go. Go, 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 go. Yay!
I have an idea of how we can scale this up a little bit. What I've got here is a fire extinguisher attached to a tricycle.
Balloon car.
But with a little more pressure involved. So
let's try this out.
now the balloon cars used a jet of air to move. There's lots of other things around that use jets of air. A fire extinguisher, a jetpack, and a jet.
Woo!
Don't try this at home. Just make a balloon car at home. Instructions to build your own balloon car are on the Design Squad website.
All right, so when we think about how they use the design process, their goal was to make a car go straight. We call that the criteria, and that's an important term we think about engineering is what's our criteria and then what's our constraints. So their criteria was they had to have a car that went straight and traveled in a straight line, and their constraints were it had to be powered by a balloon, and they only had a certain time period and certain materials to use. So they used the design process. When that criteria, when their car wasn't going straight, they did a redesign. And that goes back to that iterative process of testing, modifying, seeing if it works, testing, modifying, seeing if it works, to continue to improve the product until it meets the specific need. And so again, I want to highlight as we leave this section, the key is with your students to think process. So not about what they create, not about how beautiful it looks or how well it works, but can they go through the process? Now, granted, end product is important, but it's not the be-all, end-all. And so when you evaluate your students, really be thinking about their growth in understanding how to use the problem-solving method, or sorry, the engineering design process, rather than just what they are able to produce. And so when we think about STEM, engineering is a big piece, but when we think about engineering, we also have science, we also have technology, and then finally math. And so we'll talk mostly today about engineering, but know that the STEM acronym kind of embodies all of those. Some of our lessons are going to have a big S and a big E, so a lot of science and a lot of engineering. Some of ours are going to be heavy on science, technology, engineering, but light on math. So if we think about building using tools and materials to build a device that uses sound to solve the problem of communicating over distance, that one may be heavy in technology, science, and engineering, but light in math. There's probably not a lot of math involved. But other times we're analyzing data to see if a design solution works as intended. We may be charting graphs. We may be looking at the distance things travel. There would be a lot more math involved. So when we think about STEM education, engineering is going to be maybe the center of that, supported by science, but usually it's framed around solving a problem. And then we also have, there's another acronym that people use is STEAM, so including the arts. So an aesthetic aspect of the project. So educating students in the STEM subjects prepares students for life, regardless of the profession they choose to follow. Those subjects teach students how to think critically and how to solve problems, skills that can be used throughout life to help them get through tough times and take advantage of opportunities whenever they appear. And so I think about this quote by Stephen Dean. I can't say his last name very well. Sorry. So I think about this quote. I think what's critical is this idea that that the skills help students be prepared for life, and that it's not just about learning a content. It's about a soft skill, something that they can transfer. Maybe people may call them 21st century skills, things that they can support going forward. And so when we think about how do we know what engineering lessons to teach, the great thing is that our next generation standards, and we call them the Arkansas K-12 standards here in our state, outline a lot of the places where engineering can be incorporated. And so again, we talked earlier in our SEP webinar about the science and engineering practices. So the first one, asking questions, and then the defining problems. That defining problems is our engineering practice. And then down at the sixth one, designing solutions, is another time where engineering comes out. So most of these are science practices, but we use them, the same concepts, in engineering as well. And so when we look at standards, in our standards, anytime you see an asterisk at the end of a standard, right there, this little asterisk, that's going to tell you it's an engineering standard. And this one is talking about using tools and materials to design a structure that reduces the warming effect of the sun. And so they'll give you a clarification statement, but you can see that there's a design. So that's going to be an engineering challenge. And usually stuff like tools and materials would be, tools can be stuff like scissors and tape, or scissors and other tools that kids may need. And it's also going to be down the practices they're going to talk about, where it's defining problems, or to go a little bit deeper in that. So here's another example from 4th grade. Generate and compare multiple solutions to reduce the impact of natural earth processes on humans. So in this one, we're actually just brainstorming ideas. So students really aren't generating, or so they're not creating, they're just generating ideas. And so it could be that you actually are creating something, but a lot of times in these, we think of them more as thought exercises where students are drawing posters or creating ideas that could solve those problems. And so when we look at a chart like this, here's your grade levels on the left, and then going across, it tells you the different standards that have engineering embedded into them. So kindergarten has physical science standards and earth science. And then as you see, you go across the columns, you can see the rows. And then also engineering is also, there's also bands of engineering standards that sit outside, because the engineering standards is also one of our disciplinary core ideas, another component of our standards. So there's tons of research on what to build. I won't read all these, but just talks a lot about the importance of construction and playing. So whether it's makerspace activities or designing for a specific solution, it helps students with their social skills, their problem solving, and their spatial abilities. Again, there's tons of emphasis on hooking kids early into the STEM fields. And that this is something that kids can improve on. This isn't a set skill. If you work on it and you have opportunities to develop, you can learn more spatial and design features over time. So we're going to watch this little short commercial to think about, what type of student are we trying to build and grow in our schools?
Molly, can you please take out the trash? Hey, Molly?
longer exist. Recessive traits degeneration.
How's the new movement sequence going?
Great. Let me show you.
Please do.
I reprogrammed the robots to do the inspection. It's running much faster now. See?
That's amazing, Molly.
Thank you.
So Molly's a great example of that design process, right? So she's using planning, conducting, testing to create. And we think about the jobs that our kids are going to be working in the future. They need to be able to have those skills of creativity and be able to use this process to help them to learn. So there's tremendous amount of free resources we're going to go through quickly that you can use in your classrooms. Literature is one of the best places I think I've found to engage kids in this, hooking them into this idea. So Rosie the Revere or Violet the Pilot, The Most Magnificent Thing are all great books for introducing engineering to students. And I also want to highlight, just like Molly, each of these are examples of females doing engineering. So for so long, there's a disproportionate ratio of the number of engineers that are males to female. And when you think about engineers are designing and creating things used by all of us. And so having more females in that design world would be really powerful and important. So just encouraging our elementary students specifically to get started in engineering, to hook them into this design idea, and that they can too be creative. And it's not just for the boys. There's also Better Lesson has tons of engineering lessons you can dive into. Teaching Engineering has a plethora of K-12 engineering resources. Here in Springdale, we have our Lake Fayetteville mobile learning program, and this is one that comes out to, this is a 4th grade example. We come out to your building and we build a tsunami in a big tsunami generator, and students try to design tsunami-proof houses. And so here's some examples of students working to design. And again, it goes back to that criteria and then the constraints. And so we talk about those things in this lesson as well. I just want to be just be mindful and just to be cautious that there's a lot of things that have STEM on them. And though they may be creative craft projects or makerspace activities, not all of them are really true STEM engineering things. So just Pinterest is a great place to find activities. I just say proceed with caution. So, and here's a great example. On the left-hand side, we have the March Madness STEM basketball shooter. And granted, you can learn things like length through cutting the length of straws or measurement or distance, but it really is more of a craft project, right? So kids are building exactly the same thing. Where on the right-hand side, in the STEM roller coaster challenge, students are designing their own STEM roller coasters. And so obviously there's going to be a lot more design that goes into that, testing it, does it work, making modifications. And if every student set out to make one of those, it probably would not look the same. And I think that's just something that's important to think through, is which would require more problem solving as you're working through that. EIE is a great online curriculum that has some paid curriculum, but it also has a free after-school curriculum that they consider an after-school curriculum. But you can also use some of the lessons in your curriculum time, and it's called Engineering Adventures, and that's free from EIE's website. Here in Springdale, we use the Picture Perfect Science book series as part of the foundation for our curriculum guides. And so many of these STEM lessons are embedded into the curriculum guides from these 2 books. However, there's additional STEM and engineering lessons that can be found in those texts. And then again, EIE has an actual paid curriculum. They're expensive, but I do have one here at the office that people want to check out on pollinations. It's good for 2nd grade, but there are other ones that if you wanted to find some funding in your building and implement one of those specifically, you're more than welcome to. So just to wrap up, STEM education supports but does not replace science instruction, and especially engineering piece. If you see an asterisk at the end of a science standard, that tells you it's going to be an engineering standard. And the key is to think about teaching kids the process, not about the product. And I kind of talked about this with the Molly video, but to support the future of our nation, the seeds of STEM must be planted early, along with the seeds of literacy. Together, these mutually enhancing interwoven strands of learning will grow well-informed, critical citizens prepared for a digital tomorrow. And so know that here in Springdale Schools, we really want to emphasize the importance of STEM education and of teaching kids the engineering design process, allowing multiple opportunities for maker education or tinkering, and know that there is not one specific way this has to be done, that there are multiple paths and avenues to teach kids. There's more resources than we can even incorporate into our curriculum guides. And so know that the curriculum guides are not a be-all, end-all. There's tons of additional resources that will take your students deeper into the curriculum guides and help them to have a better understanding of these engineering design processes. If your team would like help implementing a new STEM project, I would love to work with your team on doing that, and just look forward to supporting our teachers as we continue to grow students who are prepared for STEM careers.